All right, let's take a look at question 12.27. I've got A and B set up here. And the first one, there's no chiral center in the molecule, so we don't have to worry about assigning any stereochemical configurations. But if you remember, when we talked about naming an alcohol, we have a primary alcohol here, the first thing that we want to do is find the longest carbon chain that contains the hydroxyl group. And so since it's a primary alcohol, we could start by numbering that carbon as carbon 1. We can go 1, 2, 3, 4, 5, or we could go 1, 2, 3, 4, 5. Either way, we end up with the same numbering and the same number of carbons in the longest chain, and we end up with a propyl group either way. So if we just look at the parent chain, we've got 5 carbons, so that would be a pentane. We have a hydroxyl on carbon 1, so that would be a 1-pentanol. So we could write that down. We've got 1-pentanol, and we've got a propyl group on the second carbon, so that's a 2-propyl. So when we put all that together, we've got 2-propyl, 1-pentanol. And there you go. The next one's a little more complex because we have to assign the stereochemical configuration at the chiral center. So let's see if we can do that. If we take a look at this compound, we've got hydrogen in the back. That will be our lowest priority. The oxygen will be the highest priority. You can see that this isobutyl group would be second and the methyl group would be third. So we're going from 1 to 2 to the 3 like that, which is clockwise. Our hydrogen is in the back. And so this stereocenter has an R configuration. So now we can erase all this spinach. Okay, we can get rid of all that and get on with naming the molecule. So we have an R stereocenter. Again, we find the longest carbon chain that contains the hydroxyl group, and we want to give that hydroxyl group the lowest possible number. So we'd go 1, 2, 3, 4, 5, or you can go 1, 2, 3, 4, 5. Either way, you end up with the same answer. So this is some kind of 2-pentanol. So we know it's that 2-pentanol. And we have a methyl group on carbon 4, so that's a 4-methyl. So if we put all of that together, we know that this is R4-methyl 2-pentanol. Pentanol, like that. There you have it. Let's take a look at C and D. In C, when we're looking for the parent, remember that a phenol can be a parent. So just to make sure that everybody knows what a phenol is, when we have an aromatic ring with a hydroxyl, that is called phenol, right? And we spent some time talking about phenol in the last lecture. So you can see that you have a phenol right here, and we can assume that the carbon that has the hydroxyl on it, we can assume that's carbon number 1. Now, when it comes to numbering the rest of the carbons, we can either go counterclockwise 1, 2, 3, 4, 5, 6, but that gives our first substituent 4 as a locant, whereas if we went in reverse 1, 2, 3, 4, then we give our first locant the number 2, which is lower than a 4. And so the way that I have the numbers right now, would be the correct manner for numbering the phenol. So again, our parent is going to be phenol, and we've got a 2-bromo as a substituent, and we've got a 4-methyl. So we could put that all together really quickly. We've got 2-bromo, 4-methyl, phenol. Remember that we have numbers and letters separated by hyphens, and numbers separated by commas. But since since methyl and phenol are both letters, there's no separation there. So it's all one word, methyl phenol. So 2-bromo, 4-methyl phenol. I'm going to erase this just so I don't confuse anybody. All right, last one's the trickiest of all because we've got 2 chiral centers to be concerned with here. Now, this is some kind of cyclohexanol, right? The longest carbon chain that contains the hydroxyl is 6 carbons, so this is a cyclohexanol. But we need to, and so that means that this is carbon number 1 and this is going to be carbon number 2. So we've got a 2-methyl cyclohexanol. You could even write that down now if you want. But let's see if we can determine the stereochemistry at the 2 chiral centers. We'll start with the first one. So this is stereocenter number 1, the one with the hydroxyl on it. This is going to be number 1. We've got a proton in the back. Oops. There we go. A proton, which is going to be number 4. This is going to be number 2. This will be number 3. So we're going from 1 to 2 to 3, like that, which is clockwise. And so the stereochemistry at the first chiral center is R. So we could write that down. We'll write it like this. We'll put 1 R and 2, which is this carbon here. Let's see if we can figure that out. We've got our hydrogen coming out in front. So we've got this as being our lowest priority group. This would be our first, this would be our second, and this would be our third. So we're going from 1 to 2 to 3, like that, which is clockwise, or sorry, is counterclockwise. So that would be S. But since our hydrogen is coming out in front, that would also be R. So we've got 1R, 2R, like that. I'm just going to erase this spinach just so it becomes a little clearer. So we've got both of our stereocenters as having an R stereochemical configuration. We've got a methyl group at carbon 2, so we've got a 2-methyl. So this compound is 1R, 2R, 2-methyl, all one word, cyclohexanol. And there you have it, folks. That is the name of the compound. 1R, 2R, 2-methyl, cyclohexanol. Only, there we go. Perfect. All right. Give me a thumbs up if you follow me on those two, or stop me if you have a question. Of course, you can interrupt me at any time during the lecture, and I'd be happy to answer any question you have. All right. All right. Thanks, Courtney. Good. Excellent. Well, let's move on and try the next one, which is 12.28. Let's see here. Let me find it in my textbook. There we go. So we have the first one is, let me move down here. So this is 12.28. I find these a little simpler, where you're given a name and you have to draw a structure. Usually students find these simpler too. And again, I know that nothing is simple in organic chemistry. So we have two, or cis, 1,2-cyclohexane diol, right? And we know that they're cis. So if we draw a cyclohexane, which is our parent, there we go. If we have 1,2 hydroxyls, because it's a diol, so that's a double alcohol. If they're both on the same face of the ring, we could draw them both as dashes or both as wedges. But either way, that means they are cis because they're on the same side. Again, you could draw both of these as wedges. There's nothing wrong with that. And that would be completely correct as well. Either way, that's cis 1,2-cyclohexane diol. The next one is isobutanol. This is a common name. B is isobutane. Oh, well, you should know what an isobutane group is. So when you have this as your group, okay? So that's an isobutyl group. So isobutyl, I wrote it kind of small there. And so if we want to write out the structure of isobutanol, we're just going to have an alcohol that is attached to an isobutyl group. So it's going to look something like this. You've got, here you go, and then you're going to have your hydroxyl over here. There's isobutanol. C is 2,4,6-trinitrophenol. So 2,4,6-trinitrophenol. Remember that when you have NO2 like this is a nitro group. It's one of the functional groups that I brought up towards the end of our discussion in functional groups in chapter 2 in organic chemistry 1. So a nitro group. So if we have a phenol as our parent, remember that the carbon that has the hydroxyl attached to it, that's carbon number 1. So if we number them 1, 2, 3, 4, 5, 6 like that, on the second one, we've got a nitro group. On the fourth one, we've got a nitro group. And on the sixth one, we've got a nitro group. So 2,4,6-trinitrophenol. The next one has a stereocenter in it. D has a stereocenter. It's R22 dimethyl 3 heptanol. So we know that the parent has 7 carbons and it's got a hydroxyl on the second carbon. So it's kind of not my neatest writing here. Oh, there we go. I'm missing the number 2. 2,2-dimethyl 3 heptanol. So let's draw it 7 carbons. So 1, 2, 3, 4, 5, 6, 7. In fact, let's do it like this. 1, 2, 3, 4, 5, 6, 7. On the third carbon, I've got a hydroxyl. And over here, I've got 2 methyl groups. So put them like 1 and 2, right? And just to be doubly sure, it goes 1, 2, 3, 4, 5, 6, 7. So my numbering's correct, but you can see I've got a chiral center that I conveniently ignored, didn't I? So what I like to do with these is, when I was learning the subject, what I would do is this. I would just start by drawing a wedge or a dash and then check it. If it's okay, I'd leave it, and if it's not, I'd erase it. So let's see, is this an R or an S stereocenter? So just doing this a little bit quicker, the hydrogen's in the back. This is going to be our highest priority group. This will be second. This will be third. So we're going like this, which is counterclockwise. So that is S. In order to reverse it, the stereochemical configuration, we're going to have to flip the wedge to a dash. And so we'll do that. So there's my eraser. There we go. Oops, I don't know what else I erased. There you go. So it'll look something like this. Then you can double check it if you really want to. So you've got a hydrogen coming out. You go from 1. Remember that this carbon is attached to carbon, carbon, carbon. This carbon is attached to carbon, hydrogen, hydrogen. So this is our tiebreaker here. So we go from 1 to 2 to 3. So we're going 1, 2, 3, which is counterclockwise, which is S. But of course, we reverse it so that it's R. And so our drawing is correct the way that it is right here. So let's erase all the spinach and just revel in the beauty of this perfect structure. All right, let's take a look at the next one, which is ethylene glycol. Ethylene glycol is one of those common alcohols that all students should be able to identify. Ethylene glycol. Ethylene is just this, right? That's ethylene. So if you turn it into a glycol, you're adding 2 alcohol groups to it. So this molecule where you have a hydroxyl here and a hydroxyl here. Everybody should know the structure of ethylene glycol. If you've studied biology, and I know that many of you have, you would have seen, something like this where you have a triglyceride. So everybody should know what the structure of a triglyceride is, right? This is just a fat, right? And then when you hydrolyze a fat with sodium hydroxide, and this is something that we'll look at later, not only do you end up with, in this case, you'd end up with 3 carboxylates, but you also end up with this molecule. So you have 1, 2, 3 carbons, and you have hydroxyls on all of them. And this is called glycerol. Glycerol, which again is a byproduct of fat hydrolysis. All right, the last one, F. Let me move down here, my pen. The last one is S. S2-methyl 1-butanol. S2-methyl 1-butanol. So look, here we go. We have 1, 2, 3, 4 carbons. Did I leave the number 1 out? Yes, I did. So I'll fix that. 1-butanol. Like that. So we have 1, 2, 3, 4. We put our hydroxyl here. We number our carbons 1, 2, 3, 4. The chiral center is going to be the one with the methyl group on it, right? It's going to be carbon number 2 would be the chiral center. So let me delete these numbers so we don't get confused. So for deciding whether this should be a dash or a wedge, oops, I didn't mean to do that. We could just start by drawing it as a wedge if you want, like that. That way you have the hydrogen in the back, like this. The hydrogen will be the lowest priority. This would be third, this would be first, this would be second. So we go from 1 to 2 to 3, like that, which is counterclockwise. And so that is S. So our stereocenter is correct, the way I had it drawn from the get-go. And there you go, S2-methyl-1-butanol. So that was question, what, 12.28.